In this tutorial, we're going to take a look at some of the area, perimeter, surface area, and volume important concepts for the EQAO Grade 9 academic test. And in the first 2 pages, I'm going to talk about formulas. On that test, you do get a full formula sheet, so you don't have to memorize all the formulas, although it's a good idea to be very familiar with them. And then the last 3 pages will take a look at some examples of using those and the kinds of questions that you see typically on the EQAO test. There is a set of practice questions with answers that will be, if you look in the description for this video, you'll see them. There's links to them so you can download those and try those practice exercises. I do eventually hope to have a video explaining all the solutions, but I'm not quite there yet. So first of all, we're going to start with the cylinder. This is the volume formula for a cylinder. You need to know the height, or how long it is, and the radius of the circle on either end. And so the volume is pi r squared h, and the surface area is 2 pi r h plus 2 pi r squared. Now the 2 pi r h is called the lateral surface area. It's the area, the part around. Like if you were holding a cylinder, like if you think of like a paper towel, the inside or something like that, the part you're actually holding is called the lateral surface area. And then there's the two circles in the end. So here's one circle here, and there'll be another circle down here, and that's the 2 pi r squared in the end. So the pi r squared is a circle, but there are 2 of them, one on either end. So for example, if you had a cylinder and it only had one end, then how we would change this is there will only be a single pi r squared in the end. There wouldn't be 2 of them. So if you had one end but one end closed but one end open, that would be the surface area. And if you had no ends, then we would get rid of this completely, and it would just be the 2 pi r h. That would be the surface area. Second one's a cone, and so if you have a cone with the same radius or area of the circle on the bottom and the same height as a cylinder, then it takes 3 of these cones to fill up that cylinder. Or in other words, the volume of the cone is 1/3 the volume of the cylinder. So that's why these 2 formulas look so similar. Pi r squared h, pi r squared h divided by 3, because this one's 1/3 the size. Sometimes you'll see somebody write the formula like this, so this actually means the same thing. Sometimes you'll see somebody write 1/3 in front. Okay, so I guess I should write v equals. And then the pi r squared h. So that does mean the same thing, because there's an implied multiplication right here. So now for the surface area, you also need to know the slant height to calculate, and this would be the lateral surface area here, the part that, it's like an ice cream cone. If you're holding an ice cream cone, this is the part you're touching. And so sometimes we need to calculate that. You might be given the h and the r, and you can calculate that using Pythagoras' theorem. I will take a look at that in a couple of the examples. So that's the volume. This is the surface area. The pi r s is this part here. The pi r squared is the single circle on the bottom. And of course, the surface area with no end, if the circle's open, would just be the pi r s. A sphere. So this is supposed to be a sphere like a volleyball or a basketball, and there's only one dimension. It's just r, the radius, the distance from any point on the sphere to the middle of the inside, okay, the center of the sphere. So the volume is 4 pi r cubed over 3, and again, sometimes you might see somebody write this as 4/3 pi r cubed. That's the same thing, same idea as the cone up here. And the surface area is 4 pi r squared. Kind of looks like the area of a circle formula. In fact, the pi r squared would actually be the area of this circle in here. Kind of interestingly, if you compare the area of that circle to the surface area of the whole sphere, the surface area of the whole sphere is actually 4 times the area of that circle. So it actually takes 4 of those circles to cover the sphere. Now, the volume of half a sphere, for example, if you cut it in 2 and we just wanted to know what the volume would that be, we would take this, the 4 pi r cubed over 3, and multiply it by a half. Now I just want to show you how the formula will simplify. You see this 2 will divide into that 4, and of course goes in twice. So you actually could write that as 2 pi r cubed over 3. So notice if you compare this, to get half of the volume, you're really just taking half of the 4. Now you can use this formula too and then just divide it by 2. That will give you exactly the same thing. I'm just showing you how the formula changes. Same idea with the surface area. If we only had half a sphere and we don't want the area of the circle on the bottom, like if you cut this in two and we just want the surface area, the part on the outside, then take this and divide it by 2. And of course the 2 goes into the 4 twice, and so we would get 2 pi r squared. So that would be the outside surface area of half of the sphere. So 3 more figures on this page here. And I seem to be talking completely about the 3-dimensional figures, except at the bottom here we're talking about circle. And we will talk about a little bit about perimeter and that kind of thing in a few of the examples too. So it's not just volume and surface area. So we have a rectangular prism up here at the top. The volume is the length times the width times the height. So there's the length, width, and height. And the surface area is 2 times the width times the height plus the length times the width plus the length times the height. So what each of those are the area of the one of the 3 size of sides. See, WH would be the dimensions on this, so it might call that the right side of it. And of course, on the across from on the other side would be another one of those. That's why there's a 2 here. The LW here would be the bottom and the top, and of course the LH would be the front and the back. So see, this is L by H high, so that's the front face, and there's one in the back has the same size. Now that's the formula as written on the EQAO formula sheet. If you multiply the 2 in, you're actually, this is just distributing, this is a little bit of algebra. 2 times each of these, remember you got to multiply all those by 2. The nice thing about writing the formula that way is if you have one of the sides you're not going to include. So for example, let's say there is no top. Okay, it's called an open top box. Okay, let's say there is no top there. Well, the dimensions of that top are L times W, length by width. So you see, that would mean that, you see, this is the 2 top and bottoms. So I wouldn't want to include a 2 here. I would just want a single LW, because if there's no top but there's still a bottom, then I'll still need one of the LWs. So this is how we would tailor the formula in that case. So there's only a bottom and no top, so I don't want the 2 there. And of course, if you wanted a surface area with no top and no bottom, you would get rid of that part completely, and it would just be 2WH plus 2LH in the end. So that would be this side, the one on the left, and the one on the back. No top, no bottom. Okay, so that's how you can tailor the formula if you have some sides that you're not including. Last one here, last 3-dimensional diagram, is a pyramid. This is a, well, some people call it a square-based pyramid. That's only if the L and W are the same dimension. If these L and W are the same size as these L and W in the prism up here, and it's the same height as this one, I've tried to draw it like it looks like that, then the same relationship between these is, well, it's the same relationship between that cone and the cylinder on the last page. It would take 3 of these pyramids to fill that up. So that's why this length, width, height volume is length, width, height divided by 3 for the pyramid. I didn't write out the surface area formula for the pyramid here, and that's because it's probably simpler just to find the areas of the 4 triangles and then plus the area of the base, rather than making up a formula for it. There is a formula on the formula sheet if you want to look at it, okay, but I didn't bother doing it here because I think it actually complicates things a bit if you put that into a formula. Just find the area of all the 5 faces. So one last set of formulas here, and this is for the 2-dimensional circle. Again, you only have an r, radius, so area is pi r squared, circumference is 2 pi r. If instead of having r you have the diameter, you could actually change this into just pi d. That's another version of this formula, so that is equivalence. You actually can write this as pi. See, remember, diameter is the same as 2 times the radius, so that's why we can multiply those 2 and write it as d. So pi d is the same thing. So area of a half a circle, we would just take our pi r squared and divide it by 2. Now there's nothing to divide out like there were in some of the formulas from the previous page, so we just leave it as pi r squared over 2. And the circumference of half a circle, if we want like the distance for half a circle, then we could take our 2 pi r and divide out the 2, and it's actually just pi r. Now the thing about if you do the pi d formula, then you would just write it as pi d over 2, and that would work out to the same thing. So on to page 3, and the first of a few examples. I think there's 5 altogether here. So in this figure shown over here at the right, we've got this cylinder and a cone, and the area of the bottom of the cone is the same as the area at the end of the cylinder. And we're told that it has, same base area and the same height. And so we're asked what the volume of the combined figure would be. Now we're told the volume of the cone is 40. Remember, this volume is 1/3 of this, or we could say that the cylinder is 3 times the volume of the cone. So we don't need to know any dimensions. We don't need to know how long the cylinder is. Its volume would just be 3 times the 40. So if there's 40 up here, then the volume of this would be 120 cubic centimeters. And so if we want the total volume, we just add the volume of the cylinder to the volume of the cone, and the volume would be 160 cubic centimeters. And good idea always to put an answer statement. Example number 2. We got this baseball field constructed as shown. The outfield part is a semicircle. So this is actually half of a circle exactly right here. And we're told the fencing costs $15.25 per meter. And you're asked to find the total cost of fencing for the field. This would be a pretty normal task on the EQAO, probably not a multiple choice question, because it's something you have to show some work for. So on the diagram, I'm going to draw, and this would be the diameter of the semicircle. I'm going to find D, and then of course the radius is half of that. So in this triangle right here, that D would be the hypotenuse because it's opposite the right angle. So that's the longest side in this right triangle here. So I would write my Pythagorean theorem like this: D squared, longest side, squared, equals 80 squared plus 80 squared. And of course each of the 80s squared are 6,400 or 6,400. And if we add them together, we get 12,800. To solve for D, we take the square root of the 12,800, which gives us, to the nearest meter, 113 meters. So it's 113 meters across here. So to get the radius, I'm going to work with the radius, we divide that by 2, so the radius is 56.5 meters. So remember, the circumference of half the circle, remember that formula from the previous page, is pi times r. Remember the whole thing is 2 pi r. If I get rid of the 2, then I'm talking about a half a circle. So this is the semicircle circumference formula, distance along there. So I just multiplied the 56.5 by pi. So it's 177.5 meters along the edge of the outfield here. So the perimeter of the whole object, we would add 80 plus 80 plus this 177.5, that's the distance all the way around, which is 337.5 meters. Now we want to know the cost. So every meter costs $15.25. So we'd multiply this by 15.25. And so that's what the fencing would cost before taxes, $5,146.88. On to example number 3. The figure shown here is a half sphere ice cream scoop. So the red thing is, maybe it's strawberry, sitting on top of an ice cream cone. And we're asked, is it possible for the ice cream to melt and completely fit in the cone? So we're talking about volume here because we're talking about the capacity of what it can actually hold. So we're given the dimensions of the cone, and of course the sphere's radius would be 7. And so we want to find the volume of the hemisphere, the half a sphere, and the volume of the cone. And so now remember, that was the volume of a sphere. If we want half of it, we divide the 4 by 2. So it'll actually be 2 pi r cubed over 3. So that's going to be the volume of the hemisphere. So we substitute 7 in place of r, and the volume of the ice cream half scoop is 718.4 cubic centimeters. Now we want the cone's volume. And so we fill in 7 for r and 15 for h, and we get a volume of 769.7 cubic centimeters. So notice that the volume of the cone is a little bit larger than the ice cream, the half sphere, so this could theoretically all melt and fit in the cone. To actually get that to physically happen would be a challenge, because the way the ice cream melts, it melts from the outside, so it's not actually running inside, but okay, that's another problem. This is actually the calculations in my graphing calc. I'm just showing where the 718.4, and this was the volume of the cone right here. Interestingly enough, I wanted to show you this before we go on to the next example. If you change it and make this, the height, equal to the diameter, okay, so 14 instead of 15, see the diameter across here would be 14. If you make that 14, it's interesting, so notice I changed my 15 to a 14 for the cone. The two volumes work out to be exactly the same. So it would exactly fit in, it would just be level with the top of that cone. Example number 4. A cylindrical container isn't large enough, so Jim decides to make it 3 times as big in radius and twice as high. So he's changing 2 different dimensions by different amounts. And we're asked, what is the ratio of the volumes of these 2 cylinders? So it's a cylinder, so here's the volume formula, and we'll get into the ratio for a second. So this is what it kind of looks like. We've got this container, which is pretty small. So we're making it 3 times as big in radius. So see that diameter or radius, well actually this diameter would equal 1, 2, 3 of these, and it's twice as high. So this dimension has been doubled. It's twice as high. So notice it does look a lot bigger. It's not like it's probably going to be twice or 3 times the size. It's much more than that. So here's my volume formula. And so the bigger one, this one here, see there, it's 3 times the radius. So the radius has been replaced with 3r because it's 3 times as big. And it's twice as high, so I changed the h into 2h. Okay, the h has been doubled. Now, we're actually going to use the formula to figure out how many times bigger it is or what the ratio of the 2 volumes would be. So when you square 3r, remember that actually means, I'm going to do this over on the right side here, 3r squared. Now, 2 ways you could do this. You could write 3, okay, the squared means there's a 3r times another 3r, which would equal, now 3 times 3 is 9, and then r squared, so it's 9r squared. Or you can also write this as everything in the brackets is squared. So you see the 3 gets squared, and so does the r. And of course, there's my 9 right there. So, and either way you look at it, it's going to be 9r squared. So that's going to change into 9r squared. Okay, I just took the brackets off. It's all multiplied. Now, when you multiply all these terms together, 9 times 2 is 18. And then we've got pi r squared h. Okay, so pi is a constant, so we just leave as pi. I'm leaving the r squared as r squared, and the h is h. Now, what I want you to compare is this. See, notice that the original volume is pi r squared h. See, this is actually the original volume. So this formula down here is actually saying that the volume is 18 times the original. So that means that the volume of this is 18 times bigger than this one. So the ratio, and of course there's 2 orders to write the ratio. If I write it small to large, then it's 1 to 18. If I change it around and write large first and small second, it would be 18 to 1 instead of 1 to 18. But either way, the larger one is 18 times bigger than the smaller one in volume. So that's example 4. Turning over to example 5 next. And this last one, we're asked to find the volume of this, and it's called a truncated cone. A truncated cone is when you cut the end off. So this is the part that's been cut off. So we're trying to find the volume of this part right here. So it's really a big cone that has had a small cone removed from the end. And so what we're going to do is we're going to find the volume of the whole cone and the little one on top and subtract them, and that will give us the volume of what's left. Now we're given some dimensions here. The truncated cone is 12 high, and then we're told that the slant height is 15.8, but we don't know the entire height here. So we're going to find that by using the fact that we do know S and the radius. You see, this would be 10 right here. This would be 5 here because the whole diameter is 10. And so we can use Pythagoras' theorem to find that height. So I think I mentioned in that we're going to find S, and when I was talking about the cone. In this example, actually we know S is the 15.8, and we're going to calculate the height, but we're still using Pythagoras' theorem to do that. So the 15.8 is the longest side. The h, and remember this is only 5 down here, are the shorter two sides, so that's why it's h squared plus 5 squared would equal the 15.8 squared side. So if we square 5, we get 25. We square 15.8, we get 249.64. And then so I would bring the 25 over and subtract it from the 249.64 and get 224.64. And then we take the square root. So the height of the cone works out to, it's almost exactly, so I'm rounding it to 15 centimeters. So this is 15 centimeters high. So before the cone was truncated or had the top cut off, it was 15 centimeters high. So we're going to find the volume of the whole cone. So we're going to put, see, the radius would be 5 and the height would be 15. And so we go pi times 25 times 15 divided by 3. And the volume of the whole cone is 392.7 centimeters cubed. And we're doing the small cone, this little guy on top here. So you see, this is 12, and the whole height is 15. So 15 minus 12 is 3. This height of the part that was cut off is 3 centimeters high. And we're told that the radius is 1 centimeter. So 1 here and 3 here in the formula. So basically, those 3's actually divide out. 1 squared is 1, so it's really just 1 times pi. So that's why it's pi, 3.14. I rounded to 1 decimal place. I didn't bother write the 4 because this one has 1 decimal place. And so the truncated cone's volume, we would subtract those because this is the whole thing minus what we're taking off. And so the truncated cone's volume would be just under 390, 39.6 centimeters cubed. And that's the end of the tutorial.